All right. Hello, everybody. Welcome back. We're here to continue talking about the construction of Lebesgue measure via the Riesz representation theorem. This is part two of the series, however long it's going to be. I'm not 100% sure. Um, I will link part one in the description so you can go check that out first. I recommend it since it gives an overview of what's happening here and some suggested preliminaries because I won't be doing all the preliminaries. Um, I should mention that upon reviewing Rudin's text here, especially chapter one, I discovered that indeed he does build up almost everything from scratch, including the set theory algebra, the definition of topology, what a metric space is, all that stuff. It's pretty complete. So, if you want to just read the book's got you covered. Um, but yeah, I'm trying to walk you through it and tell you some interesting and what I consider to be important points. Um, so the first time, what I did was I told you what the general plan is, like how the Riesz representation theorem works. Well, I didn't tell you how it works. I told you how we'll use it to construct a big measure, and then after that, or as well as that, I gave all this prerequisite sort of stuff that gets used in the proof, just so you know sort of the basics of what you need to know. And then I went through some basic definitions of sigma algebra and a measure, positive measure specifically, and how you define the Lebesgue integral or the abstract integral. Let's see. Yeah. Um, okay. Yeah. I guess. Yeah, okay. It is called Lebesgue. It's called a Lebesgue integral, even though the measure doesn't have to be the Lebesgue measure. So I think, something missing from that video was like, do you have any examples of sigma algebras and measures and stuff? So so let me give an example. Um, So if we let x be, let's just say like the natural numbers, okay? And we let m be the power set of x. So that's uh, the set of all subsets of x. Then this is a sigma algebra, all right? If you review those conditions, I did actually say it verbally that the power set is always a sigma algebra. Um, and then we can define mu of E to be the number of elements in E for E finite, or infinity if E is infinite. Okay, so this is known as the counting measure. Okay. So, it's a little bit of a trivial measure, but it is a measure. You can think through like how do you know this is countably additive? And that will just come down to checking the countable additivity is pretty easy to see if you think about it. If you have a countable collection of disjoint finite sets, if infinitely many of them are uh, are non-empty, then then you have an infinite number of elements in the union, and the sum will converge to infinity, or diverge, however you want to put that. Um, and then obviously, if only finitely many of them are non-empty, then you're just looking at, the number of elements in the disjoint union is the sum of the number of elements in the individual sets, right? It's pretty easy to check, basically. So anyway, this is an example of a measure. It's a pretty cool one. Um, and it gives you an idea of how you can connect uh, like Lebesgue integrals with, say, a discrete sum, right? If you think about it here, like the integral of a measurable function here, every function is measurable, by the way. An integral, the integral here is simply going to be the the infinite sum, right, of the values, right? So that actually gives you, back to that merchant's bill kind of example that I gave in the first video. Okay, so I wanted to show you that, and then I wanted to present, let's see, a couple of things from chapter one here. So let's look at next page here. Let's look at, let's say this is going to be a sort of lemma. Let's call it a lemma. So if mu is a positive measure um, on a sigma algebra M. So you can think of the previous example if you want. I mean, what I'm about to say is pretty obvious in that case, but anyway. Um, then let's see. Then we have if A1 is contained in A2 is contained in A3, and so on. Um, and these are all in the sigma algebra M. Then the measure of the union is equal to the limit as n goes to infinity of the measure of the individual ANs. Okay, so that's basically the statement here. Again, going back to what I said in the first video, you can clearly see from this that calculus is a requirement for understanding this. And calculus, like what is a limit, is I'm about to say is something that Rudin doesn't talk about, but I'm not so sure about that actually at this point. Let's see. Uh, let's see. Are limits defined? I think they're not, but I could be wrong. I don't see a definition for limit. So I think that is something um that he's assuming that you've seen before. Anyway, how do we prove this? And the proof is pretty funny. The main point here, obviously, is that if you have a disjoint union, you know that um, the measure of the disjoint union is equal to the sum of the measures of the individual sets, right? Now, this is not a disjoint union. It's sort of the opposite of that, right? It's a nested union, right? These sets are contained within each other. So if we're going to use the only property we know about measures at this point, then we're going to need to get some disjoint sets, and it's pretty easy to do that. So what we do here is we define bi to equal ai minus ai minus 1. Okay. It's fairly straightforward definition. Um, it should be easy for you to check, oh, and I'll just say B1 is equal to A1 since there is no, or we could say A0 is infinity, but anyway, who cares? Then these are all in M, okay? And that's easy to see because BI here is just equal to the intersection of AI with the complement of AI minus 1. All right. And we know from the definition of sigma algebra that sigma algebras are closed under um, complements and countable unions. Um, which implies, so if you take the complement of this, what you get is AI complement union AI minus 1. Both of those are in the space, right? In the sigma algebra, right? So then the union is, I mean, we can, the transition from a countable union to a finite union is pretty easy. I'm not going to go over that. But that means the complement is in the sigma algebra, and therefore this set must be because the complement of the complement takes us back. So so now um, we have these BIs. The BI are disjoint. All right. And that's just because of the nested union, right? So like if we take this one and subtract this one, then it's going to be disjoint from all the stuff up here that gets A3 subtracted. And of course, it's going to be disjoint from everything down here, right? Because we're subtracting A2. So we're subtracting all of the sets down here. So anyway, it's fairly easy to see that the BI are disjoint. Um, AN is equal to the union I equals 1 to N of BI, and the union I equals 1 to infinity of the AIs is equal to the union I equals 1 to infinity of the BIs. Okay? And the BIs are disjoint. So that is actually a disjoint union. And that means we can apply um, the one and only property, right? Countable additivity of a positive measure. So that means the measure of um, the union from I equals 1 to infinity of BI is equal to the sum I equals 1 to infinity of measure of the BIs. Okay, which is in turn equal to the limit as n goes to infinity of the sum from I equals 1 to n of the measure of the BIs. That's just by uh, the definition of an infinite sum. So yeah, just going back to basic calculus. Okay, and then this is then equal to the measure of an, right? By that second sum, because this is also a disjoint union. It's a finite disjoint union. Like I said, going from countable to finite, it's pretty easy. Just take the empty set a bunch of times. Feel free to think about that if you want. But basically, this has to equal that. And so we get this. And then let's not forget that this is equal to the union of the AIs as well. Okay, so QED, right? That's our result right there. Okay. So that's a cool thing to have. Okay. Um, and then what I want to do from there is I want to talk about the monotone convergence theorem. So let's talk about Lebesgue's monotone convergence theorem. Okay. So so Fn measurable functions on X. Okay. So in this context, we have uh we have a sigma algebra. So with sigma algebra M and measure mu. So this generally doesn't get mentioned. I think Rudin doesn't specifically say this, um, but it's pretty clear. Um, uh, yeah, yeah. It looks like yeah. He gives a yeah. There's a long discussion of how to phrase all this, but anyway, you get the point. We have a sequence of measurable functions. Okay. And suppose that A, the FNs are increasing. So, for each X. Okay. Okay. And B, uh, the limit as n approaches infinity of Fn of X is equal to f of X for all X in X. Okay. Basically means the same thing as what I wrote here. Sorry, I just fell into my little habit there. So for every basically is what this means, or for all. So anyway, the upside down A, just a little shorthand that I sometimes use. Then F is measurable, and more excitingly, the limit as n approaches infinity of the integral Fn d mu is equal to the integral of f d mu. So you can bring the limit inside the integral. And I should note here that this is pointwise convergence. Okay. Generally, when you're dealing with Riemann integrals, you kind of need uniform convergence for good things to happen. Um, but with Lebesgue integrals, this is something that's very useful, and I invite you to I invite you to show that this does not hold um, that this does not hold for the Lebesgue for the Riemann integral. Right? So try to construct a sequence of functions that increases and converges pointwise to f, but that uh, but where the Riemann integral does not converge to the Riemann integral of the limit. Um, so I think I think you can come up with examples for that. That's an interesting problem to think about. Okay. took a little pause there to think about it. So I think actually something that's worth pointing out at this stage is the uh, the most interesting part of all this is that f is measurable. So uh, it turns out for the Riemann integral, if f, the limit function, is Riemann integrable, then the integral will converge, right? So actually, this is not a problem. It's this that's the problem. The limit could easily just not be integrable at all. And I invite you to come up with examples of that. It's actually pretty easy. Uh, it's pretty easy if you think of a function that you know of that you can that is not Riemann integrable, and then just try to realize it as a pointwise limit of Riemann integrable functions. I think if you do that, it's not so bad. I think usually you can see how to do that. Okay, so anyway, that's the theorem. Okay, and so let's do a proof here. Okay. So, uh, by by an earlier theorem, f is measurable. So let's go back to that. Um, okay. So, note since the each fi, or what am I trying to say? Um, since since fn x is increasing, we have that f of x here is equal to the supremum over n of fn of x, right? So if you have a monotone sequence, monotone increasing sequence, then the limit is equal to the supremum, right? Which is the least upper bound. Okay. Um, so uh, so uh, So let's just try to see that this is measurable. Okay. Um, and let's consider um let's um consider f inverse of the interval from alpha to infinity. Okay. Uh And we can include infinity if we want. I don't want to get involved in all that. So remember what I'm trying to show? What I'm trying to show here is that the inverse image of every open set is is measurable. Okay? So if I can show that the inverse image of this one uh, set is measurable, then then what I can do is use some complement tricks um, to um, to show uh, to show that intervals the other way are also measurable, and so that'll prove it basically. So basically, I just need to show this one set is measurable. And This is basically equal to the union n equals 1 to infinity of Fn inverse of the very same interval. Okay, so how do I prove this? So let's just go let's go in the two directions. So if x is in Fn inverse of alpha to infinity, then that means that Fn of x is between alpha and infinity, and therefore, um, since uh, f of x is greater than or equal to Fn of x, we have that x is in F inverse of alpha to infinity. And now I guess I see why we have to include the other endpoint here. So I'll just go ahead and tack on that um, to make it official. Okay. So similarly, if x is in F inverse of alpha to infinity, then alpha is less than f of x is less than or equal to infinity. And for n large enough, uh, Fn of x will be greater than alpha, right? Because that converges to f of x. So therefore, x is in Fn inverse of alpha to infinity, including the right-hand endpoint. Okay. So, I would have to assume that that the value of f is finite for every x, which I can assume. I mean, if you want to keep um, if you want to keep these if you want to keep the square brackets like out of the game, all you need to do is basically assume that this limit is finite for all x. If you assume that limit is finite for all x, then there's no problem, right? Then all the fn's are positive, or sorry, all the fn's are finite for all x, and then we can just put the round bracket on the end and not include infinity in all this. Rudin wants to include infinity for generality, I think. The proof is basically the same, so I'm not gonna lose my mind about it. But that basically shows that f is measurable, right? Because each fn the fn's are measurable. So these are measurable sets, meaning they're in the sigma algebra, and that means we can take the countable union. So this is a countable union of measurable sets done. All right. So that takes care of f being measurable. Interestingly, that is the harder part, or I shouldn't say the harder part. It's sort of the part that isn't true for the Riemann integral context. Um, but it does. So now we know why f is measurable. So we need to explain why the integral converges the way that I want it to. Okay. So since these these integrals here are increasing, we have that the limit as n goes to infinity of the integral exists in the interval from 0 to infinity, including possibly infinity. Okay? Because just because f of x itself is finite doesn't mean the integral is finite, Okay, so this sequence could increase to infinity. That's okay. We're going to allow that for sure, right? I don't know if I want my functions to take the value infinity, but I certainly don't want to rule out that my integrals could be infinite. That is very much a possibility that we want to allow. Okay. Obviously, if we assume that f has a finite integral, then we get a finite result here. But let's just let alpha be the limit, okay? Because it's an increasing sequence, so there's a supremum, right? It's the supremum of this. Okay, but the reason why I say that is because I want to show this. So the first step is I know this limit exists, and now I've named that limit alpha. So basically, I want to show that alpha is equal to the integral of f. That's my plan. Okay, so the plan is to show alpha is also equal to the integral of f. Okay, and basically, we're going to do this. We're going to do this from two sides. Um, since the integral x f n d mu is less than or equal to the integral of f, right? Just by the sequence of inequalities. So integrals preserve inequalities. That is a basic result that I haven't proven. It's not super hard. Um, so I invite you to prove that. Um, I think I think you can prove it pretty easily, shall we say. Um, okay. So uh, uh, so anyway, this means that alpha is less than or equal to the integral of f. Okay, so we have the inequality going one way. So we all we need to do now is we need to prove the inequality going the other way. Okay. All right. So the other way is a little bit more involved, but not too bad. Okay. So let's get into this. Um, let S be a simple measurable function such that I write that a lot. S is between um, 0 and f. Okay. So it's worth noting at this point that it suffices to show that the integral of s is less than or equal to alpha, right? Because remember from the definition of the Lebesgue integral of f, it's equal to the supremum of all of these. So if all of these are less than alpha, then the supremum is less than or equal to alpha, and therefore we get the inequality facing the other direction. Okay, so basically this is all we need to show. Okay, and that's going to be our task. Okay, so now let C be uh, between 0 and 1. So this is just to push our problem a little bit down. If we let C between be a number between 0 and 1, first of all, it's not 0, which is handy. But second of all, it's less than 1, but it can be as close to 1 as we want. So in the end of this, we can let C approach 1. Okay, it's like we want C to be 1. But the results that we need don't work for C equals 1. So we're gonna let C be less than 1 very slightly and then use a limit to plug the gap. That's our plan. Okay, and define. So we're gonna define sets En, which are equal to the set of x, so that f n of x is greater than or equal to C times uh, S of x. Okay. So, like I said, it's like I want f of n to be greater than or equal to s of x, but what I've done instead is I've let it be equal to a slightly smaller multiple of s of x. Okay. So, uh, on this set, okay, on this set, this is a simple function, okay? And so that means that on this set, right, we can consider En as its own proper measure space. We have that the integral over En of Fn d mu is greater than or equal to um, the integral over En of Cs d mu. Okay. And that constant can be brought out of the integral. You can easily see that from the definition of the integral of a simple function, right? That constant just floats as a factor in all the terms in the sum, and you can just bring it out. It's very easy to see that. So we have this, right? But on the other hand, if we integrate Fn over a larger set, then all we do is increase the size of the integral. Okay. So I think that's easy enough to see. Okay, so now we have that for all n. Okay, so now we take limits, so we let n go to infinity, and what we end up with is first of all, this will converge to c times the integral over x of s. Oops, that's not what I meant to do. S d mu. Okay, and then this converges to alpha. So now we know that alpha is greater than or equal to c times the integral of this arbitrary simple function. Okay. And you might have a question about this. Okay. So what we're doing there is we are applying a prior result um, um, about unions. So note that um, E1 is contained in E2, is contained in E3, and so on. So, go back to the definition of these ENs, right? So remember that Fn plus 1 is greater than or equal to f of n, right? So so if x is in En, x is in En plus 1, right? Just by the monotonicity, right? So remember we started off this is a monotone sequence here. I mean, maybe I should have put a third one to make that as clear as I can. Um, okay. So these are nested, okay? And the entire space is equal to the union of these EIs, okay? So let's go back to the definition. So if we fix x, right? If we fix x, um, then we know that eventually Fn of x will have to be greater than c times s of x because s of x is less than or equal to f, and if we multiply it by a number that's less than 1, it's going to get strictly smaller than f unless f is equal to 0, and if f is equal to 0, then everything's 0 here, right? Everything's 0 and it's no problem. Okay, and it would be in that En. But otherwise, then we can just use the pointwise limit to see that every point in the space is in one of these. Okay, So I'll leave that to you. But now we use the fact that this here, if we apply the integral, this is a measure. Okay. And that's actually pretty easy to see, especially for a simple function, because if you're dealing with a simple function, basically we're just like intersecting, right? There's nothing there's nothing like super involved here. Like to see that this is a measure, you just need to show it's countably additive, and you just have like a finite sum of countable, a finite sum of infinite series. It's pretty easy to see that it's a measure. So the limit as n approaches infinity of uh, this is equal to this. So that's how we get this, right? And it's just multiplied by the constant c, okay, which I'm allowed to do. And so by previous lemma. Okay. I am dodging some details, I'll admit, but that's going back to this result here. Okay. So the union is x, right? And it's the limit of those. Okay. So that proves this. Okay. Not too bad. You could also yeah, I mean we could just break it apart and prove it. Whatever. Anyway, I think you get the point. Okay, so now we have this, okay? And at this point we can let C approach 1, right? So C here is strictly less than 1, but now let C approach 1 and we get that alpha is greater than or equal to the integral of S d mu with no C there. And so that's the end, right? That's all we needed to do, right? Recall, that is what, where did I say that? Uh, that is what our goal was. I know I said that at some point. Oh, here it is. Suffice to show this, right? That's what we just showed, right? Here it is. It's flipped the other way around, but it's the same inequality, right? Less than or equal to alpha. Alpha is greater than or equal to. Okay. So that's the monotone convergence theorem. I wanted to show you that because I want you to get an idea of why the Lebesgue integral is so useful. And that's one of the big reasons. And there's a whole collection of results like the monotone convergence theorem, like the dominated convergence theorem, a series convergence theorem. There's Fatou's lemma. There's a whole bunch out there. And I'm not gonna like go into all those because this isn't like a complete sort of video, but I thought it was worth introducing. Um, I thought it was worth introducing that to you. Okay, so now what I want to do is I want to move to some topological stuff. So let's look at some topological preliminaries. Okay. So uh yeah, there's so much that I want to say here. Okay, so X is going to be locally compact Hausdorff. Okay. I don't want to tell you what that means. But I invite you to go check um Rudin for the definition of that. Yeah, every point of X has a neighborhood whose closure is compact. So you can see this in Rudin, or you can just like Google locally compact Hausdorff, and you can get a good sense of that. Then we have some notation. So CCX is the set of all continuous real valued functions. I guess it doesn't matter. F from X to, let's say, R continuous with compact support. Okay, so this is a set of all continuous functions with compact support. Okay, support. So the support is equal to the set of all x, so that f of x is not equal to 0, but it's not quite that. It's actually the closure of that. Okay, so this is a closed set, um, uh, and we are assuming that this is compact. Okay. So I told you topology was required here. I just feel like if I go over all of that, we're going to get way bogged down in an intro topology class, which is just too much for me to really contemplate right now. Okay, so that is the continuous functions with compact support. Continuous means what it usually means. And then we have K less than F. So what does this mean? This means K is compact. So K is a compact subset. So K compact. Um, F is a continuous function with compact support, not necessarily equal to K. 0. So F is between 0 and 1, and f of x is equal to 1 for all x in K. So that means K is a subset of the support of F. For example, okay? So this is a notation that we're going to want to use when we get to the Riesz representation theorem. So I just want to tell you what that means. So saying this is a shorthand for all that. K is a compact set. F is a continuous function with compact support. It's between 0 and 1. And f of x is equal to 1 for all x in K. Okay, so the other one we have is f is less than v. So this means that V is open. F is, again, a continuous function with compact support. It's again between 0 and 1. So some of this stuff is in common. And this means the support of F is contained in V. Okay? So if X is in the complement of V, then F of X is equal to 0. Okay? Just a little consequence of that, right? The support is all the x's where f of x is not equal to 0, and then we take the closure. So it's even larger than that, but in particular, it contains every point where the function is not equal to 0. So if you're not in that set, if you're not in the support, then the function has to be equal to 0 there. Okay? That's just kind of a comment, but I think it's good to realize that. Okay. So now we have this, and so let's talk about the Rudin Eurozone lemma. Okay, so X is locally compact Hausdorff. Okay, um, V is open, K is compact, and K is contained in V. Then there exists an f that's a continuous function with compact support such that k is less than or equal to f is less than or equal to v. So both of those are true. Okay? So if we look at the previous page, we sort of compare what's happening here. You see that k is contained in the support of f, and the support of f is contained in v. So we're finding a function whose support is like nicely balanced between these. Of course, f of x equals 1 for all k is different from saying this, but nonetheless, there's a nice balance here. Okay, so you might be familiar with the regular Eurozone lemma. So regular Eurozone, which says that if x is normal, metric spaces are normal, then if A and B are disjoint closed sets, then um, uh, then there exists f from x to 0, 1, continuous, such that f of x equals 0 for x in A and 1 for x in B. Oops. Oops. Okay. Okay. So uh all right. The reason why I say that is um I want to explain to you how you can get it from the regular Eurozone, in case you've seen that. Like if you've taken a basic Poinsett topology class, you should have seen the regular Eurozone limit at some point. It's also basically the same as the TC extension theorem. Um, so let me just show you how you do this, because I think this is cool. So now if X is locally compact Hausdorff, um, K is a subset of V, right? So compact, open, okay? Then there exists a U open, um, um, let's see. Yeah. Such that K is contained in U, is contained in U, closure is contained in V, and U closure is compact. Okay, so that's something that you should be able to prove without too much difficulty, as long as you're familiar with what all this stuff means. Okay, So it's a classic kind of separation thing. Um, and it does take some doing, honestly. I spent a while on this, just ironing out the details, but I think getting into the weeds here is a bad idea. I just want to give you an idea of how you construct this. Okay, so now consider X star. So this is the 1 point compactification of X, which is therefore compact, Hausdorff, which is therefore normal. Okay. So, I mean, all of that requires justification. And what do I mean by the 1 point compactification? Basically, you add 1 point and you make it compact. What more do you want from me? You can definitely look that up. That's in Monk too. So if we consider that, then by regular Eurozone, we have a continuous f from x star to 0, 1, such that f is equal to 1 on k and f is equal to 0 on the complement of u. Okay? So now we can observe that um, so f is equal to 0 on the complement of u. So thus the set of x such that f of x is not equal to 0 has to be contained in u, which is contained in u closure, and therefore the support of f is contained in U closure and is therefore compact, right? Because U closure is compact, and closed subsets of compact sets are compact. Okay, so f has compact support. Okay, and then uh, uh, and then uh, we can um, we can easily observe. So remember what we wanted from all this, right? We wanted the function to be 1 on k, and we wanted it to have support contained in v, right? Remember, those are the conditions we wanted, right? So we wanted both of these. So I mean, we have this, we have this, we have this, we have all of this stuff. We have that, and we have this as well. Okay? Now this is on X star, so now to finish, restrict F to X, right? So F naturally has domain, the 1 point compactification. Just restrict it to X, and boom, you have the function that you need. Okay, so that's just showing you how to get Rudin's version of your zone's lemma from the regular one. Um, I just say that because Rudin basically reproves the Eurozone lemma just to do the case that he needs here. And that proof is involved. I mean, it's not the worst, but like I said in the last video, it's a tougher one when it comes to um, point set topology. So anyway, now you see. Um, Now you see how that goes. Okay. And the next thing I want to talk about is partition of unity. So let V1, V2 out through Vn be an open cover of K, which is compact. Okay. Then there exists Hi less than Vi such that the sum from I equals 1 to n of Hi is equal to 1 on K. Okay. And so here, this is all going on in a locally compact Hausdorff space X. Okay. So it's basically a finite partition of unity. At a certain point, when we prove the Riesz representation theorem, we need this finite partition of unity. Um, so let me show you how this proof goes. Okay. So for each x in K, there exists open Wx such that X is in Wx is contained in the closure of Wx is contained in um, Vi. So remember, the union of the VI's contains K. That's what open cover means. So if X is in K, then it's in some AI. I'm sorry, it's in some VI, and therefore there's some open WX whose closure is contained in VI. Uh, that's not obvious, by the way. I mean, that's something, the locally compact Hausdorff thing is playing a role here. Um, this is compact as well. All right, so this is related to what I did in the Eurozone. Um, uh, the Eurozone stuff that I just got through talking about. So now we have one of these for each x and k, which means that the w's form an open cover. So that means we have by compactness there is a finite subcover. So that means that K is contained in uh, a union, a finite union of these WXIs. So I'm going to call them WX1 through WXN. So these are N points that are in K, but these W's um, actually cover K. Okay, and so by compactness, every open cover has a finite subcover. That is the definition of compactness. Okay, um, so we get this, and now let HI equal um, the union where WXJ closure is contained in VI of WXJ. Okay. Oh, we're taking closures here. Okay. So that's HI, okay, which could be empty. All right. So each one of these W's we know is contained in some VI. Okay, so we just take the ones that are contained in every particular VI and we take the union of those. Okay. But it's okay if HI is empty, I'm not worried about it. This is compact. Okay, because it's a finite union of compact sets. Even if it's empty, it's still compact. Okay, so but and clearly by construction, it's a subset of VI. So by Rudin Eurozone, there exists GIs that are greater than hi, but less than vi. Okay, so far so good. Vi is the open cover I started with. Hi are these compact sets that I constructed. Okay. Um, Now define h1 to equal g1, and h2 is going to be 1 minus g1 times g2. And we keep going like that until we get to hn, which is equal to 1 minus g1 times 1 minus g2, all the way out to 1 minus gn minus 1 times gn. Okay. So it might not be obvious why you would do this, but you can do it, and then it follows that hi is contained, or hi is less than vi. Okay, so that means the support of hi is contained in vi. Okay, so if hi is not equal to zero, then I mean the first one's obviously true, right? H1 is contained in the support of V1 because H1 is equal to G1, and we already know this. Okay. Um, and then if hi is not equal to zero, then all of these have to not equal zero, including the last one. Okay. And and that means that that point. So the set where hn is not equal to zero um is contained in there. And also it's contained in it's more importantly, it's contained in this the support of gn, right? The support of hn is contained in the support of gn. Okay. So that means the support of hn is contained in Vn or Vi. Well, anyway, indices. Okay. So uh, that's an easy argument that you can prove this. I think you can handle it. It's not too bad. Okay. So let's go to the next page here. So H1 is equal to G1 is equal to 1 minus 1 minus G1. That's a very arbitrary and weird thing to say, but it'll make more sense when you see what I'm going to say now. So now assume that the sum of H1 to HK is equal to 1 minus 1 minus G1, 1 minus G2, all the way out to 1 minus GK. Okay, so we can put that in brackets if you want. Okay, so clearly it's true for k equals 1. We assume it's true for k, so we're trying to do an induction here. Then h1 plus hk plus hk plus 1 is equal to this whole thing. 1 minus 1 minus g2, 1 minus gk, plus hk plus 1, which is equal to 1 minus g1 product out to 1 minus gk minus 1 times gk, right? Just by definition, this is equal to that, okay? Okay, and now just a little bit of algebra here will show easily that that is equal to 1 minus 1 minus g1 minus g2 all the way out to 1 minus gk, all the way out to 1 minus gk. Um, sorry. Oh, I got my indices. My indices are off here. Sorry. That's supposed to be that's supposed to be k. So this is gk, this is gk plus 1. Okay, there we go. All right, now it makes sense. So, basically you can see uh this as a sort of coefficient here, right? And so here there's a -1 and here there's a gk, right? So if we do a double negative here, we get 1 minus gk plus 1, right? So like I could put in times 1 there if I wanted, right? Times 1, and we have a negative here. So, and that's plus gk, which is the same as minus gk plus 1. So anyway, that's basically how that works. Okay, so now we have this formula, okay? Since uh, K is a subset of H1 union out to Hn, okay? So, uh, remember how we constructed the HIs? We constructed them like this. So we take all these W's that are contained in VI. We know that the W's cover K, right? The W's cover K, okay? And each W is contained in some VI, okay? So as long as we account for all the VIs, we will have to contain every point of K, right? So K is a subset of the union of the HIs. For all X in K, there exists a GI such that um, GIX equals 1, right? So so if X is in K, it's in some HI, okay? And remember, remember where all this came from. So if it's in HI, right? Then that means GI of X is equal to 1, right? Going back to what this means, okay? And if GI is equal to 1, right? If GI is equal to 1, then then this sum here, which holds true for all n, by the way. So h1 plus hn, which is equal to 1 minus g1 out to 1 minus gn. Okay. So if gix is equal to 1, then this is actually 0. All right. So just this equals 0 in that case, right? And if that's 0, then h1 plus all the way out to hn, right? The sum of all the h's then. So that implies that h1 plus hn x equals 1 for x in k. Okay, so that's why we set it up like that. Okay, and that gives me my finite partition of unity. Okay. Okay. So that's my topological preliminaries. Those are not the only things that you need to do to prove all this stuff, but I thought it was worth sharing that with you, just so you see how we get down to the nitty-gritty and do some real math. So given the time that I've used here, I think the wise move for me at this point is to call it. And so next time, I will actually state the Riesz representation theorem in full, and I will start to prove it. I'll see how far I get before I run out of steam or the video gets too long. But as always, ask any questions you have in the comments. I'm happy to either comment if it's possible or make a video addressing any question you have. I want to share this stuff with you. So, if you want me to do like a whole video of like topology basics, I can do that. I just don't want to do it if it's not particularly interesting to you and you already know that stuff and you kind of just want to see how this Rudin business works. I could also do it on, linear algebra, basic, very basic linear algebra, set stuff, whatever you want to see, or if there's just some step in what I've done here that doesn't seem to make sense, just let me know. But until next time, thank you all for watching and, happy mathing.